Good. Welcome back to your favorite inorganic tutor YouTube channel. Today, we basically look at ordinary differential equations, right? So, in this topic, we have four methods or four approaches of solving this ordinary differential equations. All right. So first, we have the separable equations, and then two, we have the homogeneous method. Three, we have the integrating factor approach, and then five. And the fourth approach, we have the exact differential equations. All right. So let's begin by the separable equations. All right. Let's begin by the separable equations. So with the separable equations, whenever we have the equations in the form dy over dx equals p of x times q of y, then we say that this equation is separable. All right, we can separate these equations into y term and then s term, right? So let's begin with this example. Y prime plus 2xy is equal to x. All right, this example is basically in the form of separable equations. All right, but then this is y prime. We have to change it back to right, dy dx, before we can separate these terms into x and y components. All right, so dy dx is equal to y prime, right? So we have dy dx plus 2xy is equal to x. All right, and now we have this in terms of this. This is how it's supposed to be. All right, and now we have it. Now let's separate this dy dx plus 2xy equals x in the form. So we have dy dx plus 2xy minus 2xy is equal to x minus 2xy, right? We subtracted 2xy on both sides to make sure that we eliminate the 2xy, right? So to make sure that we eliminate the 2xy on the left aspect, right? So we have dy dx is equal to this. We take off this, so we have x minus 2xy, right? So this, we can factor x out. We can factor x out here, and then we have dy dx is equal to x out 1 minus 2y, right? Now we can send this dx here and bring this x to this side, right? So we have dy equals x into 1 minus dy 1 minus 2y dx, right? We multiply through by dx, so this dx took off this dx, and then we have this here, right? Now we want to have only in terms of x here. So what do? We divide by 1 minus 2y. 1 minus 2y. Good. So this will basically take off this as well. And then we have 1 over 1 minus 2y dy is equal to x dx. Right. Now we have been able to separate the terms, the x and the y on the left hand side, and the x on the right hand side, right? Now we can apply what we call integration. Then we can integrate this and have our implicit form, and then later we convert it to explicit form, which is making y the subject. The whole idea is to make y the subject, right? Good. So 1 over 1 minus 2y dy is equal to x dx. Now we want to integrate this, right? So let's integrate the left aspect. So integrating this, we have integrating this aspect, we have s squared over 2. We add 1, hold on, bring the integration sign first before you do your integration. So integrating this right hand side, we have s squared over 2 plus c, right? Because we add 1 to the exponent and divide by the result. That is integration for you. Good. So from here, we want to integrate the left aspect as well. So how do we integrate this function, right? If you are fluent with integration, you will know that this will give you minus half ln absolute 1 minus 2y, right, is equal to s squared over 2 plus c, right? If you are fluent with integration techniques, you basically know that this will be this. Good. But if you are not fluent with integration techniques, let me highlight you on how I came by this solution. All right. So let's u equals 1 minus 2y, right? And then differentiating this, we have du equals minus 2 dy, right? Because we are differentiating with respect to y. Good. So now let's make dy the subject. We have dy equals du over 2, and that will be negative because of this sign. Good. So now let's say we have 1 over, because we said u should be equal to 1 minus 2y. Let's put wherever we see 1 minus 2y, let's put u there, right? So we have u times, now dy is expressed in terms of u, right? So we have times minus du over 2, right? Now let's bring the minus half out, and then we have minus half integral of 1 over u du, right? And we all know that this is a basic integration technique that you have to know, that if you have 1 over u is basically ln absolute u, right, plus a constant. All right, so this is how I came by this solution seen here. All right, so if you have any function like this and you want to integrate, just use u substitution and substitute into, in place of whatever is there, solve for it, come and replace it, and then you know what you have. All right, so basically the 1 over 1 minus 2y dy, when you integrate it, you have minus half ln absolute 1 minus 2y, right? Now, this is what we have, all right? So, what can we do? We can multiply through by minus, because we want to have the lane 1 minus 2y on the left hand side, right? So let's multiply through by minus half. You are multiplying through by minus 2, right? So minus 2 times x squared over 2 plus c. Don't forget that whatever you do doesn't affect your constant. That is a constant of integration. So whatever you do with your functions doesn't affect the constant. All right. So this will take off this, right? Because we have minus here, so it's going to be basically ln 1 minus 2y is equal to minus x squared, because this will take off this and you have minus there, so minus x squared plus c, right? This is the implicit form. This is the implicit form because we've not make y the subject yet, right? So now let's make y the subject. This is our implicit form, all right? So now this is what we have. We want to make y the subject, right? So let's go. So we have ln 1 minus 2y is equal to minus x squared plus c. Now, we want to make y the subject. So what do we do? This is base y, right? You know that ln is of base y. This is what we use in advanced mathematics when we have ln is base y, all right? So we introduce base y to both sides, and then we have, when you have this, you basically have it gone, right? Because this is going to be 1, all right? So this will now be e power minus s squared plus c, right? Very, very simple. Get it from there. When you have ln 1 minus 2y equals minus s squared plus c, you want to eliminate the ln. So what do? We introduce the base of the ln, which is the e, right? And then we have this here. So when you introduce the ln, basically the ln will go away, and then we have the expression in the ln, right? So from here, we can say that 1 minus 2y is equal to e power minus s squared plus c. And now we can subtract minus 1 on both sides, right? So we have 1 minus 1 minus 2y is equal to 1 minus e power minus s squared plus c. So basically this will take off this 1, right? And then we have minus 2y is equal to 1 minus e power minus s squared plus c, right? Now we want e to make y the subject so that we have the explicit form, right? Explicit means you want to make y the subject. That's all. Right? So from here, we divide by -2 and divide whole thing by -2. Right? So we have this taking off this, and then we have y equals 1 minus e power minus s squared plus c over -2. All right. So y equals 1 minus e power minus s squared plus c all over -2. All right. And then we know that when you have log a plus log b, we know that we can say that we have log a b, right? So the same ideology is applied on this aspect as well. So we can also write this our solution. We can also write this our solution as, so basically when we subtracted -1 from both sides, we are going to have minus, right? So we have y, because we are applying the basic logarithm laws, we are going to have c e power minus s squared minus 1 all over 2. All right. So this is basically going to be minus c e power minus s squared minus 1 all over 2. So this is our explicit form. All right. So it's very simple. You just have to understand the concept of integration. Please, if your integration is very weak, I advise to go back. I have a video on integration. Please currently go and watch, and then you really enjoy this topic very well. Good. So that is the solution for the problem. All right. So let's look at another example under homogeneous. Let's look at another example under homogeneous. Let's look at an example under homogeneous. Let's look at an example under homogeneous. So with the homogeneous method, it is not difficult. You have to make sure that your integration techniques are very good and you are good to enjoy this topic as named ordinary differential equation. So let's look at homogeneous method. Homogeneous method. So with the homogeneous method, when you are given the function and you want to know that this function is indeed homogeneous, what we first do is that, for instance, you have the y, the x is equal to s squared plus y squared over xy. What you first do is that you introduce variable, say k, on all the terms, right? So we have, let's check. So we have, let's say f of kx, ky. This is what you are going to have, right? So we say the y, the x should be equal to wherever we see x, we put k there, right? So we have kx all squared plus ky all squared all over kx times ky, right? So this, we can basically see that this is homogeneous because we're going to have the y over the x equals, this will give us k squared s squared plus k squared y squared all over k times k will give us k squared s y, right? So now we have the y over the x is equal to, you can see that k is common at the, k squared is common at the denominator, and k squared 2 is here as well. So we factor k squared out, we have s squared plus y squared all over k squared x y, right? So we can see that this has been able to, the number, the variable that we introduced to the function has been able to cancel out completely without leaving anything in it, right? So we can see that this function is indeed homogeneous. So now we've seen that the function is homogeneous. What next are we going to do? Let's see. So since the function is indeed homogeneous, we say that the y, the x is equal to the function, which is x squared plus y squared over xy. Now, what do? We divide each of the items. Note, we divide each of the items by the highest power of what? X. Let me take it again. When you identify that the function is homogeneous, divide each of the item by the highest power of what? X, right? So we have the y over the x is equal to s squared over s squared plus y squared over s squared all over x y over s squared, right? So good. This is what we have here. The y over the x is equal to, this will be 1 basically, because s squared over s squared will be what? 1 plus x and y squared over s squared will be, we can write it as x over y over x all squared all over, this will take one of the x, right? So we have y over x also. So interesting, right? Very, very interesting. For homogeneous, it's not difficult. Just have to pay attention and note your integration techniques as well. So now, what is next? Now that we have been able to divide each of the item by the highest degree of x, right? Then what is next? What we have to do is that let's call y over x v, right? So let's call y over x v. So we say that v is equal to y over x, right? So now, what can we do here? We multiply through by what? X. And now we have vx is equal to y. Good. Now we have to differentiate this function, obtain, so that we can have something and substitute into this expression. All right. So now, since we've called this v over v as y over x, let's place it in this function, right? So let me write that one first. So let's v equals y over x, and now we have the y over the x as 1 plus v squared. Since v is y over x, we have v squared all over v, right? Very good. So now, what can we do about this? We have to differentiate this function so that we have it something in terms of it, so that we can substitute or place into or plug into this function so that we can simplify the expression, right? So the y over the x, now we have this v equals y over x, so we multiply through by x, right? So we have vx equals y. So now let's differentiate both sides using the law of products or the product rule of differentiation, right? So from here, when we differentiate the y over the x, we are differentiating with respect to x, all right? So differentiate with respect to x, we have the y over the x from here, right? This is y equals vx, right? So the product rule says that we maintain the second one, then we differentiate the first term, right? So we maintain the second term and then we differentiate the first term. So we have x dv with respect to x plus we maintain the first one and then we differentiate the second one. So we have v dx with respect to x, right? So we have the y over the x is equal to x dv over the x. Very, very simple. So now we can see that the x will cancel the x and we have v. Very, very simple. So now we have the y over the x as this term. So now what can we do? We can substitute into equation. Let's call this equation 1, right? And call this equation 2, right? So now equation 1 and equation 2 are the same. So what do? We equate them, right? So from here, we say that the y over the x is equal to the y over the x, right? So what do? And they are equal to 1 plus v squared all over v is equal to, what is there? X dv over dx plus v. Very, very simple. Just have to understand how this came about and you are good to go, right? So from here, let's divide each of the item by v on the left hand side, not to talk of this side. Let's divide each of the item on the left side by v, right? So we have 1 over v plus v squared over v is equal to x dv over the x plus v, right? So this we have 1 over v plus this will take one of the v, right? So we have v equals x dv over the x plus v. Good. So now we have something that can be common to be cancelled, right? That can be common to be cancelled. That can be common to be cancelled, right? So from here, we can see that we have v here, we have v here. So we can cancel out the v. And now we have 1 over v is equal to x the v over the x, right? Because this has basically taken care of this, right? So from here, what do? We have to separate them. So we are coming to the method of separable method. So now we can separate these items and have v in the v and have x the x, right? So how can we do that? We can do that by multiplying this side. We can do that by multiplying this side by v and multiply this side by v, right? So we have this, taking off this, and then we have 1 equals x dv over the x. Basically, let's bring the v here so that it won't be like you're having v squared there, right? Good. So now, what can we do again? We can multiply this by the x and multiply this by the x. So this, take all of this, and then we have the x equals vx dv, right? So now we want only v dv to be here and x ds to be here. So what do? We divide through by x, and this x take all of this x, and then we have 1 over x dx equals v dv. Alright, so here, what can we do? Now we have in the form of implicit. So this is the implicit form. This is the implicit form. So now, what do we have to do? We have to make sure that we make, or now we have it in the implicit form, right? So what do? We integrate both sides. And now we have integral of 1 over x dx is equal to integral of v dv. Alright, so this, you know that your basic integration techniques, your basic integration identities, if you know them very well, you know that integral of 1 over x will give us ln x, right? And then, because this is the x, we add plus c, and then this is equal to integral of v dv will also give us v squared over 2, right? Very, very simple. So now we have ln x plus c equals v squared over 2, right? So what can we do now? Ln x plus c is equal to v squared over 2. We need v, right? So we multiply 2 by 2, right? So we have 2 times ln x plus c, v squared. But earlier on in our through the process, we said that v should be equal to y on x, right? So we can do that substitution over here, right? Very simple. So now let's go. We have 2 ln x plus 2c is equal to v squared, right? So from here, good. So we know that whatever we do doesn't affect the constants, all right? So we have 2 ln x plus c, right? Now we need c, v, not v squared. So we say that v squared is equal to 2 ln x plus c. So we square both sides. We take the square root on both sides. So square root of this function and then square root of v squared, right? So we have v is equal to plus or minus 2 square root of 2 ln x plus c. But then on our earlier notice, we said that v should be what? Y over x, right? So we say that, but v equals y on x. So let's say v equals 1 over x. So we say y over x is equal to plus or minus root of 2 ln x plus c. Good. So we have this here. What do? We need y. This is still in the implicit form. So what do? We need y to be the explicit, right? So what do? We multiply through by what? X. So we have y equals plus or minus x root of 2 ln x plus c. And this becomes our explicit form, right? This becomes our explicit form. Very, very simple. Let me write the final answer here. Y equals plus or minus x square root of 2 ln x plus c. And this is our explicit form. Very, very simple. Please, you just have to practice your integration techniques, and this topic will be very easy for you. Let's go to the next method or the next approach in solving the ordinary or the first ordinary differential equation. So the next method is the integration or the integrating factor. The integrating factor or the linear differential equation system, right? So the integrating factor, what basically you have to know is that is in the form dy over dx plus p of x y, and it should be equal to q of x. It should be equal to q of x, right? So you are asking or you are thinking about what p of x is and what q of x is basically mean, right? So what do we do? From here, we can identify our p of x and our q of x from the function that we will be given to solve, right? So from here, let's look at an example. So taking this example, dy dx plus y is equal to x, right? Make sure that whenever you are given the function and it is not in this form, you take it to this form before you use the method or the approach of integrating factor, because it should be linear. What you have to know about the integrating factor is that it should be linear, right? No degree higher a degree more than 1. The degrees in there are always 1. Good. So what do you have to do? We have to first locate what p of x is, right? So p of x over here is basically the coefficient of y, right? So the coefficient of y in here of this function is basically 1, right? Is 1y. So p of x is equal to 1, right? And then step 2, we have to identify what we call mu of x, or anything, let's say mu of x, right? What we call mu of x. So step 2, this is step 1. Step 1, you identify your p of x, and the p of x in this function is 1. So 2, you identify or you solve for your mu of x, right? And the mu of x is giving us the exponential of the integral of p of x, right? The exponential function to the power integral of p of x, right? So now we have this function mu of x is equal to the integral of 1 dx, 1 dx, 1 dx. So when you integrate 1 dx, we all know that 1 dx is giving us e power x, right? Because you know that integral of 1 dx will give us x, right? And then e, right? So we've identified our u of x, that is the mu of x, equals e power x. All right. So step 3, what do we do? Step 3, we now have to multiply whole equation by the mu of x. Multiply this whole original equation by the mu of x, right? So we have mu of x times the whole of the function, 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 right? So from here, we say that e power x, which is the mu, into the whole of the function given, which is dy over dx plus y should be equal to x. We are multiplying everything by the mu of x, and the mu of x of n is e power x, right? Good. So what do? We expand, or we split the e power x to each of the items in the brackets. So we have e power x dy dx plus y e power x equals x e power x, right? So from here, what we have to do after the step 3, the left side of our equation is equal to the left side of our equation should be equal to d over the x of the mu of x times y, the mu of x times y, or the mu of x times the y in the original function, right? Times the y. Good. So from here, what we are going to write the left side in the form this, and this is what we have, right? So this, the left hand side, we want to write it in this form, right? So we have d of dx, d over dx into the mu of x is e power x. So let's bring the y first and have y e power x is equal to x e power x. Let me clarify this part again. When you have this, right, you write the left side of the equation or the left side of the function in the form d dx into mu of x times y. Get it good. From here, you choose the left side of the equation, say d over the x times mu of x times y. Good. And now our mu of x was obtained as e power x. All right. So e power x times the y is equal to the right hand side. Good. So from here, we can now do our integration. We can now do our integration by integrating both sides. So this is the implicit form, right? Implicit form means you have both x and y on either side of the equation. Good. So from here, we integrate both sides, and then we have integral of d over dx into y e power x equals integral of x e power x dx. All right. So from here, we can see that d over dx will take off the integral sign, and then we have y e power x equals x e power x. This side, we have to use integration by parts to integrate this particular aspect, the left aspect of the function. All right. So from here, we can either use the tabular form of integration or we use the formula of integration. So now, integrating x e power x using the tabular form, we have this. Say u and v. Always choose u to be the part where you can integrate. No, choose the u part to be the part where you can differentiate for it to go to 0 completely. All right. So looking at this, which function will you choose to, take everything to 0 completely? We can only choose x, right? So we say that x should be equal to u, right? So when you integrate, so we say u should be equal to x, and then v should be equal to what? E power x. Good. So from here, we've chosen x to be u. So when you differentiate, we know that when you differentiate x, we have 1, right? And then when you differentiate e power x, we still have e power x. Good. Now, when you differentiate 1, whenever you differentiate a constant, we know that we have 0, right? And then we have e power x. This will keep on repeating itself. Good. So from here, this will still give us 0, so you don't need to write it. Good. From here, we know that this goes here, this goes here, this will be plus, this will be minus. Good. So we have plus minus, right? So this is basically plus minus. That's what we have. So here, let's say this is 0 as well again. So this will be minus. Are you getting it? So now we've identified our u and the v. So this part is not really necessary, but I just want to show you how this solution will be coming by, right? So now, from here, we know that uv minus integral of what? V du, right? Now, we know that with the formula, that is the formula approach. But here, this, we know that uv, right? So this, which is this times this, right? This times this, and that will be e power x. Are we okay with that? That will be and this will also be 2 plus minus plus. Good. So we know that then the understanding is u times v minus the integral of v du, right? So we have x times this, and that is x times e power x minus the integral of v du, right? And the v is what? E. So we have e power x, right? Plus our constant of integration. Plus our constant of integration. So if you want to use the tabular form, just have to introduce or locate your u and the v. The u must be the variable that, or the variable that when you differentiate, it will completely go to 0. So that's what we have there. We're choosing x, and then the v to be e power x. So you know that when you differentiate x, you get 1. You differentiate u power e power x, you have e power x. When you differentiate 1, you have 0, and that order. And then the operations are plus, minus, plus. Are you okay? Good. So from here, we have the right hand side as this. We can alternatively use the formula approach too as well. We know that u is equal to x, so we differentiate u and we have the u equals the x, right? And now when you integrate this, you have integral of the v, good, and you have v equals e power x, right? So that is basically what we have. When you use the formula, you have the same answer as this. So there's no difference. The table is also very simple if you really understand the table. So now let's go to the expression of thing. This is just to show you the integration, some of the integration techniques, right? So now let's continue with the work. We have e times e power x is equal to now we know the integral of x, e power x dx as x e power x minus e power x plus c, right? So that is the integral of this function, right? So we say this is equal to x e power x minus e power x plus c. All right. So from here, we have this function, and then we can say that this is the implicit form. This is the implicit form. So now let's divide each term by e power x and see what we have. Let's divide each term by e power x. Right? So when we do that, we have this taking off this also taking off this, and this also taking off this. All right. So we're basically going to have y equals 1, y equals x minus 1 plus c over e power x. All right, and then we have y equals x minus 1 plus c. With the help of indices, we can know that this is the same as c e power minus x. I hope you are not confused there. This over this is the in indices. This is the same as this. All right. So from there, from there, we can now see that we have our answer in the explicit form. So we can say that our final answer is y equals x plus c e power minus x minus 1 as our final answer. And this is the explicit form. All right. The question is very easy. I just decided to explain it very well for you to get the understanding so that any other problem that will be put forward, you'll be able to answer. All right. So basically, the idea of the integrating factor, the separable method, the homogeneous method is to make the y the subject. And that is the explicit form that we are talking about. Are we okay? Good. So now let's look at the last technique, that is the exact differential equation. All right, the exact differential equation. The exact differential equation. The exact differential equation. The exact differential equation. The exact differential equations. So this is also it is in the form of, this is in the form of m of x and y dx plus n of x, y dy, and that should be equal to 0. That is the exact differential equation. All right. So with the exact differential equation, you have this term and you have this term as well. So we call the m of x and y, the x as m y dx. All right. So we call this aspect or this term as m y dx, and then we call n into x and y dy as n x dy. All right. So as n s dy, for this, we cannot go ahead and say that we have my, since we are calling this function as this whole function as where is it, this as this, we can see that we have my dx plus nx dy as 0, because we are calling the whole of this as this and the whole of this as this, so we can just replace them into the function, and then that's what we have over here. So now let's check this example on this approach as well. So let's take this problem, 3x squared plus 1, 3x squared plus 1 plus 3y squared plus 2y y prime should be equal to 0. All right. So with regards to this problem, we can see that this problem um it's not in the form of it's not in the standard form. All right, so we have to change this y prime to dy dx. All right, so we have 3x squared plus 1 plus 3y squared plus 2y times dy dx equals 0. All right, basically we know that y prime is the same as dy dx. All right, so that is what we do over here. And then we know that this dx can be multiplied through to have 3x squared plus 1 dx plus 3y squared plus 2y dy, and that should be equal to 0. All right, so now we have it in the standard form as the function. All right, so from here we now since we have it in the standard form we can now call this expression as my. Now we can see that my is equal to 3s squared plus 1, and also nx is equal to 3y squared plus 1. 3y squared plus 2y. All right, so that is what we'll be having. Since we have been able to express it in the standard form, we can now locate our my as this, and then our nx as this. All right, so let's continue from there. Let's continue from. So now, no, we don't have any y terms here, and we don't have any s term here. All the terms are grouped at one side. All right, so now we call the m, since there is no y term here, and since there is no s term here, we take the reason why we call this part 3 s squared plus 1 dx as my is because we will take the partial derivative of m with respect to y, and then if we, the reason why we are calling this part 2 as n is because we will take the partial derivative of n with respect to x. All right, in this function as well. So now, since when we take the partial derivative of this function with respect to y, we are going to have 0 here, and then we take the partial derivative of this function, also we are going to have 0. We can say that my is equal to 0, and then nx is equal to 0. All right, since the partial derivative with respect to this function, we are differentiate partially with respect to what? Y. So this will be 0, and this will also be 0. So we say that my is 0, and then xs and then ns2 is 0, right? So we can say that my is equal to ns since they are all 0. All right. So this is checked to be uh, an exact differential equation, since we have been able to note that the ns part is equal to the my part. Right, good. So now since we have this, let's continue and then go ahead to integrate all the items. It's either we pick this aspect or we pick this aspect and then integrate. And then when we integrate, we add a constant. And that constant is not going to be a constant of integration C, but rather a constant of a function. So let's say we are picking this function. So let's say we are integrating m dx. When we take the m dx, then we are going to add a function, a constant function, which is g of y. And then when we choose, or let me say when you choose to integrate this aspect as well, the n dy, then we add a constant, say a constant of a function, say h of x. Very, very simple. So in each case, you either add some function, say g of y or g of h of x, all right, depending on which side you choose. All right, so let's proceed from here. Let's proceed from here. So here the recommendation is where is it? Go back to the function and check the original function. Let's go back to the function and check the original function. Which one will be easier when we integrate? Always you have to choose which aspect will be easier when you integrate. All right. So let's take the 3x squared plus 1 dx. Let's take that aspect. All right, and integrate, because we can realize that when you integrate this aspect, it will be more easier than taking the other aspect as well. So integrate this function plus 1 dx plus a constant of the function, and that will be g of y. Very, very simple. So here, when you integrate this, we have 3s cubed over 3 plus x plus g of y. Are you okay? You add 1 to the exponent, use it, the result to divide the whole function. Here too, you integrate 1, you have x, and that's what we have here, plus the function. All right? So we have this taken off this, and then we have s cubed plus x plus g of y. All right? So now this is what we have. So what is our next step? What is our next step? So our next step is to differentiate this function partially with respect to y, because we are interested in the y or this function. All right, so we differentiate this function partially with respect to y. So this is because our main objective or our main aim is to solve for g of y. All right, so if you differentiate this function with respect to y, we have d of with respect to y. All right, so it's going to be y down here. All right, then the whole function, that is x cubed plus x plus g of y, sorry. All right, so we are differentiating partially with respect to y. All right, so when you differentiate partially with respect to y, we are going to have j prime of y, right? Because all this will go to 0 because they are constant. We are differentiating partially with respect to y, so all this will go to 0, and then when you differentiate this, you have j prime of y. So now we are going to set this to the end part of the function, right? Since we chose this to integrate, after we have everything and we differentiate partially, we equate it to the other part that we ignored. All right, so now we have j prime of y is equal to 3y squared plus 2y. All right, so now we have this. All right, we have this, and we are going to compare this function to the left side of the equation. Now, because this function is already this function doesn't have any function over here, it's going to be the same thing. All right, so we have j prime of y equals 3y squared plus 2y. All right, so we have to integrate both sides again. All right, because we are interested in the y. All right, not j prime of y. So when we integrate both sides, the y, you know that they are in terms of y, so it will be dy, not the x. All right, is equal to integral of dy 3y squared plus 2y dy. All right, so here you know that this, because of this differentiation sign, we will have j of y. This differentiation sign will take the integral sign. All right, and then we have g of y equals the integral of this function, and the integral of this function will give us 3y cubed over 3 plus 2y squared over 2 plus a constant of integration. Let's call it k. All right, let's call it k. Let's call it k. So now we have j of y is equal to, this will take off this, right? And then this also take off this. So we have y cubed plus y squared plus k. All right. So this is what we have now. Now let's substitute g of y into this function, which is the f of x y back. So we have f of x y, and we know that this is equal to the constant, which is the c. All right, this is equal to come in. So now, as we have g of y equals y cubed plus y squared plus k, we now substitute g of y, which is this function, into the f of x and y. That is basically, it was s cubed, the function we obtained, s cubed plus x plus g of y. All right. F of x and y was s cubed plus x plus g of y. All right. Good. So now f of x and y, f of x and y will be equal to s cubed plus x plus g of y plus, since we are substituting this into this, we will have y cubed plus y squared plus k. All right. Okay, good. So this will no more be here. Right. So we have this obtained. So what is next? We know that this function is equal to c, right? This f of x and y is equal to c. All right. So we replace this by c, and then we have c equals s cubed plus x plus y cubed plus y squared plus k. All right. You know, this is a constant and this is a constant, so we take one of the constants. All right. Or in other words, we can decide to call the k c2 and call this one c1. So c1, c2 minus c1 will give you c. All right. So that is basically the same thing. Because I don't want it to look the same, I just introduce a k here and introduce a c here. But because we are dealing with one constant of integration, you have to use only one. All right. So we have c equals s cubed plus x plus y cubed plus y squared. All right. So this will be our final answer. All right. So that is basically the process we go through to solve the exact differential equation. All right. It's not difficult. You just have to know your integration techniques and then you are good to go. You really enjoy this topic because you know integration techniques. Thank you very much for watching. Be expecting the next thing to come is matrices, how to find the inverse, how to find the determinant, and how to tackle how to use the Cramer's rule to solve three systems of equations using the matrix. All right. And then the analytical geometry aspects, to be expecting the circles, some questions on circles, and then I'll be tackling some questions on differentiation as well. Thank you for watching. I really appreciate you. Thank you for watching. Bye.